Hi everybody, today's video is about doing a chi-square. A chi-square is a calculation that you use after you've done an experiment because you want to find out the answer to this question here. Is the variation that occurs in an experiment due to chance, or is it actually due to the independent variable that you were testing? So in order to get going with this, we've got to talk about what your hypothesis was. So there's two kinds of hypothesis, and we are trying to either prove and justify and accept the null hypothesis or to reject it. So we often say, do we accept or reject the null hypothesis? So the null hypothesis is the really boring thing like, okay, if nothing was due to my variation, everything should remain the status quo. That's the null hypothesis. So I'm going to give you an example with the pill bugs. When we have our pill bugs, our null hypothesis is that we would expect the same number of bugs on both sides of the choice chamber. If there's bugs that are in equal number on both sides, they are not choosing either side. So randomly by chance, we should have the same number. An alternate hypothesis is what you would say if you really think something is going to happen because of the variable you're introducing. So let's say you are putting strawberry jam on one side. Your alternate hypothesis would be like, they're going to prefer the strawberry jam. All right, so when you do a chi-square, you are always going to have a null hypothesis, and after doing your calculations, you need to accept or reject your null hypothesis. All right, on your formula sheet, which you're going to be getting this week, you will have all of these formulas that we use. Some of them are statistics, some of them are calculations on water potential and all different things. But over here on the very beginning of the formula sheet are our statistical analysis. So the ways that we go through and look at data. So we're going to be talking about standard error and mean and standard deviation. Today we're focusing right here on chi-square. So the formula looks a little crazy, but I'm going to break down what that formula means. It's actually a quite simple calculation to do. And then down here are the critical values. These are the values that we're going to use to decide if we should accept or reject our final value in our null hypothesis. So here's chi squared. The letter x is chi, and it is squared, and it equals sigma, which is the sum of O minus E squared over E. O just means what did you observe? E means what did you expect? So the difference between what you got and what you thought you would get, and you square it, and then you divide that by what you expected, and you take the sum of each of the different sets of data that you have. So as we go through, I'll show you how you always set this up and how you do it. So I thought to start out, we would talk about something really simple, heads or tails. So chances of getting heads or tails, 50-50. If I went through and actually did it, I got 43 heads and 57 tails in 100 tries. So if I wanted to see, is that just due to chance? So my null hypothesis would be I should get 50 heads and 50 tails each time. And I want to see if my data either accepts that null hypothesis or it rejects it. An alternate hypothesis, if you want to think about that for a minute, you could say that maybe the way that you shake or maybe the way that your hand lets it down, that you're more likely to get one or the other. Or it could be something where you're worried that maybe a coin is weighted differently, like maybe at a poker game or something. I don't really know how to play poker, so not a good example. But all right, so if I click on the next screen, I actually set up these cell shades so that I can show you piece by piece how you set it up. So there's certain things that we're going to have to record. Observed, what did we observe? And expected, what did we expect to get? And then in order to get to that sigma O minus E squared, I have to do O minus E. And I have to do O minus E squared, and I do O minus E squared over E. And then over here in these rows, I need heads and tails. So this is how you're always going to be setting up a chi-square calculation. The thing that will be different each time is what you have over here, because that's based on the data that you're looking at. So for example, for pill bugs, you might have the number that went on the wet side versus the number that went on the dry side. All right, what did I observe with head and tails? I had 43 heads and 57 tails. What did I expect? First of all, when you add this up, it totals 100, and I would expect half the time to get heads and half the time to get tails. So I would have expected 50-50. If you subtract 43 minus 50, you would get 7, and some of you might be saying, oh, you would really get -7, and that's okay because as soon as you square it, those negatives would positive out. So 7 times 7 is 49, and then I take 49 and I divide it by 50, and I get 0.98. Now over here, I do the same thing with the tails. So 57 minus 50 gives me 7. 7 times 7 is 49. 49 divided by 50 is 0.98. Now, if at any time during these videos you want to pause and do the math yourself and make sure you're getting the same values that I get, I would totally encourage that. Now, you remember in our formula, it said that chi-square is equal to the sum of these values. So I have to take these two numbers, add them together, and I get 1.96. So 1.96 is equal to chi-square. I now have finished the math, but I haven't accepted or rejected yet. So I have to figure out, am I going to accept or reject my null hypothesis? So what I do is I first need to figure out degrees of freedom. Degrees of freedom means you take the number of possible outcomes. So I had heads and tails, 2 possible outcomes, and I subtract 1. So I have 1 degree of freedom. So here on the chi-square table, I'm looking at 1. This is the probability. It's called a critical value, and we use a probability of 0.05. And you can think of that as like, I'm 95% certain that this was due to chance. So to be 95% certain that it was due to chance that I got 43 and 57 when I should have gotten 50-50, my value would have to be less than the critical value listed here. So I had 1 degree of freedom. I am looking in this 0.05 column, so the critical value that I need to be less than is 3.84. I am far less than that, so I am going to accept my null hypothesis. Mine came out within the realm of acceptable. All right, let's try another. I just made this up. I said, hey, what's the chances that when we walk around and let's say it's a Friday and everybody's got on Ranger t-shirts, what are the chances of students wearing Ranger t-shirts that are the blue background or gray or white or gold? And I say null hypothesis, chances are they are going to have the same the probability will be the same of each color. An alternate hypothesis, if you want to think about that for a second, you might say, oh, no way, there's way more white shirts that are Ranger shirts, or there's way more gray or blue or gold, whichever one that you think. So I want to go through some actual data. So here we go. White shirts, I counted 29 Ranger shirts. Gold Ranger shirts, 18. Gray Ranger shirts, 22. And navy blue Ranger shirts, 21. So this is the data that I got. And next, I set up my chi-square. So right now, you might want to pause it. Go ahead, do all the numbers yourself and see what you get. White, gold, gray, and navy blue are my 4 possible outcomes. Over here, observed, expected, observed minus expected squared, observed minus expected squared over expected. So if I go through, and actually I might be able to do, oh no, if I go through, I put my observed, let me cover this again. All right, what do I need to do to actually find out what I would have expected? And what I need to do is I need to count up these numbers and find out how many kids did I actually look at their shirts. So when you add 29, 18, 22, and 21, you get 90. And if I expect, due to my null hypothesis, the chances of each of them to be equal, I would take 90 and divide it by 4. When I do that, I know I would have expected 22.5 kids to have on a white shirt, a gold shirt, a gray shirt, and a navy blue shirt. Then I go through and I subtract. For this one, I got 6.5. When I square that, I get 42.25. When I divide that by 22.5, I got 1.88. For gold, the difference is 4.5, which squared is 20.25, which over 22.5 is 0.9. For the next one, that's only 0.5 of a difference. It's very close to what was expected, which gives me 0.25, which gives me 0.01. Navy blue, a difference of 1.5 squared equals 2.25, and over 22.5 gives me 0.1. Now you go through and remember chi-square is the sum of each of these values. So I need to take this last column and I go 1.88 plus 0.9 plus 0.01 plus 0.1, and I get 2.89. That is my chi-square value. Again, I need to accept or reject. So I go back to my chart from our formula sheet, and first I need to calculate the degrees of freedom. Well, there were 4 possible outcomes. It could have been a gray shirt, a white shirt, a navy blue shirt, or gold. So I take those 4 outcomes minus 1. I want to go in the 3 degree of freedom column. So here's the critical value that I need to be lower than, 7.82. I think mine was 2.89, so I'm lower than it. So again, I'm accepting the null hypothesis. The chances were, and it worked out with my data, that it fell within a normal range, that it's pretty normal for kids to have on any of those different Ranger t-shirts at any one time. All right, so here's our bugs. This is the lab that we are doing this week. So here they are in the wet chamber and the dry chamber. What's the null hypothesis? So I'm hoping that you're thinking about what would I have expected if it was just boring and simple. The boring and simple answer is it's going to be the same. The same number of bugs on the wet side, the same number of bugs on the dry side. So you're going to actually go through and do a chi-square based on the data that you get. So you're going to average out how many bugs were on the wet side each minute, how many bugs were on the dry side each minute, and compare that data, set up a chi-square, and see if you accept or reject your null hypothesis of them being equal. I also wanted to throw one of these on here. It's going to come up much later in the year, but it's really where chi-square is also very, very prevalent. You will see it used all the time with genetics problems. And we're looking at this cross. So right here, this is like an old Mendel cross with the green pea plants. And you cross 2 of these green pea plants and you end up with 1/4 of them being yellow. So looking at the data, you see that green is dominant, but both of those green pea plants were carriers, which means they were heterozygous. They were big G, little g. So 25% of the time, their cross yielded a yellow plant. So I went through and I am giving you some pea plant data. I'm telling you that I grew a whole bunch of pea plants this summer and I did the cross, and my outcome was 620 of the pea seedlings were green and 105 of the pea seedlings were yellow. And I want you to figure out, first of all, what would the null hypothesis be? And I want you to see if you accept or reject it. So I want you to go through and put in the observed. I want you to figure out what you would expect and then go through and do the calculation. So here you want to pause the video for a moment, do your math, and then come back. All right, so you're back. So I have entered my observed was 620 and 105. I then add those together and figure out that that was 725 plants total that I was using. To do expected, I expected 3/4 of the plants to be green. So I take 725, the total, multiply that by 0.75 or by 3/4, and I get 543.75. So that's what I fill in my expected column right there. For the yellow, I take 725 and I multiply it by 0.25 or by 1/4. So I would have expected 181.25 to be yellow. I go through and I do the math. I get these answers. To do chi-square, I find the sum of these bottom 2, 42.77. I then go to the critical value sheet. And I had 2 possible outcomes, green and yellow. So 2 outcomes, I need to be under this critical value of 5.99. I am not under that value, so I am rejecting my null hypothesis of the chances of green and yellow being the same. All right, my last slide here says practice. I have a lot of practice in the animal behavior task packet, and I think that you become great at these calculations by practicing them. So make sure each time that you come up with your null hypothesis, you actually make your table, you fill in all the values, you do the math, and then you check it with the critical value from your formula sheet, and you accept or reject.